Hopefully you found that lecture on the history of life somewhat interesting. To continue on that piece with the history of life, you gotta have evidence. Evidence, remember, is always very key in science. We like to support the things that we say, which doesn't go for most of you guys in class. But in terms of the evidence, there's two main pieces that I'm going to give you. We're actually going to talk about. Well, I'm going to talk about today. The first one being stromatolites, which is layered rock. Stromatolites are these rock-like formations. Like as you can see here, there's like a sea of stromatolites. A sea of stromatolites in the sea. But anyway, these are rock-like structures that are formed by cyanobacteria, which cyanobacteria are considered the first life forms on Earth. And we'll get into that in one of our future lectures. But if you've ever seen these around, you think, oh man, it's a bunch of rocks in the ocean. Nope, these are stromatolites. And then everyone's favorite, fossils. Fossils are any evidence of an organism from, at least evidence that that organism lived a long time ago. And there's different kinds of fossils, which we'll kind of dabble in, I'll talk about in this lecture. But the thing about fossils is fossils are able to tell us some really important things, including information about how old an organism is or was, and the appearance, like when did they first show up? Because like depending on where you find that fossil, you can kind of gauge like, oh man, it was like 1,000,000 years ago versus like 100,000 years ago. Also, because of this, we're able to determine past events on Earth and how organisms changed over time. So here we have a Tyrannosaurus rex. If you've never seen a Tyrannosaurus rex skeleton, you've sorely missed out. Especially in Chicago, Field Museum of Chicago had Sue. Sue was this crazy Tyrannosaurus rex. But enough about Miss K's stories. See, you even get the Miss K stories when I'm doing lectures online. But examples of fossils. So we have amber, which is like a fossilized tree sap. Best example I can give you of amber is if you've ever seen Jurassic Park. They have the insect, the mosquito that was in the amber. They extract the mosquito, extract the DNA from the mosquito, because of course mosquitoes have always been blood drinkers. Happen to have the blood of a dinosaur within the mosquito, and then we were able to create Jurassic Park. Trace fossils. Trace fossils are fossils that show us traces of your organisms. So here's the original over here, and we're actually going to be looking at some squatting dinosaur tracks. If you look at this same picture, just magnified so you can see everything, you can see the pelvic imprints of your dinosaur. Its tail, how it was dragging here, went from here and then dragged around here, as you see your organism walking away, shuffling its feet. We also have petrified fossils, which petrified fossils are just wood saturated with minerals. Because the wood is saturated with minerals, it gets hard. Petrified, have you ever heard of the petrified forest? It's out west. Basically, I think, if I remember correctly, this is a really good picture of part of the petrified forest where these aren't actually rocks. These are just, it's wood that is now petrified and it's very hard. We also have imprints. Imprints being like that trace of life, like if you've ever done like rubbings in like art class when you're like in kindergarten, almost the same deal, but it's a shallow impression of an organism. Then we have molds, which are like deep impressions of an organism. So like this definitely you'll see if you're trying to excavate certain areas, like you might find a really deep impression, like shells. And if you have molds, you also have casts, which is basically a filled-in mold. Because like if you look at that last one, like here's your shell, and then here's your cast, where oh look, it's filled in. And like a lot of the skeletons that they do, especially like the ones you might order from like a biological supply warehouse. The fossils, the skeletons they give you are actually casts. And then you have your true form fossils, which when most people think fossils, they think things like this. Okay, one of the most important things to remember about fossils is that a lot of the time they're found in sedimentary rock. which maybe, hopefully, ideally, you've taken some type of earth science class when you were in middle school. But in case you didn't know what sedimentary rock is, it's formed when certain particles, they're compressed, hardened over time. Remember, Miss Case is more so the life science, but I do remember there's igneous rock, sedimentary, and I feel there might be another one, but next time. But for fossils to form, you have the organism, it's buried, and then over time you have mud, sand, clay, some type of sediment that forms over it, hence sedimentary rock. But then, in terms of fossils, it's like people were like, okay, here's a fossil, this thing lived so many years ago. How can we use fossils to tell how old something is? Well, there's two different ways. The first one being relative dating. And this is what I was saying when I was like, oh, okay, fossils can tell us how old something is. It doesn't actually give you the age, like, oh man, this is like 1.5 billion years old. Relative dating works out because, okay, you have the layers of the Earth, and depending on where you might find a certain fossil, is kind of that obvious, like, okay, well, if it's closer to the core of the Earth, well, it's an older fossil. And if it's closer to the surface, then it's something younger. So it can only tell us, like, if you found two fossils in the same exact area, you can go, okay, well, this one's older than this one. The second one we have is radiometric dating, and the actual age can be determined because we use certain radioactive elements. Half-lives. For example, I'll give you this radiometric dating of a fossil, where, remember, I told, like at the beginning of the school year, we kind of talked about in our biochemistry unit how C14, it's like this radioactive carbon, it's an isotope of carbon that we use to date things, because all living organisms absorb C14. So eventually that organism turns into a fossil, and radioactive carbon, C14, decays at a certain rate. Because we know that rate, we're able to date, paleontologists are able to date the fossil by measuring the amount of C14 it still contains, like after the fact. So if you follow this flowchart here, living organisms absorb C14, eventually become a fossil. Small piece of the fossil is burned and converted to carbon dioxide gas. So when it's converted into carbon dioxide gas, we're able to pull, okay, stable carbon, which is the normal carbon that you see in your periodic table, atomic mass of 12. And then you have the unstable C14, the radioactive carbon. That is what we measure. This further decays into N14, which emits an electron, because nitrogen is typically, that's just the way it is. And then a radiation counter records the number of electrons emitted. So depending on how many electrons you emit, you're able to kind of determine C14. And unfortunately, if I had the time, I would have brought one of my BFFs out. He's currently doing some paleontology work. He's been doing that for a while. But next lecture, we're going to talk about the leading theories on the origins of life. So if you have any questions before we get into this, definitely bring them to me in class, because I want to make sure everyone's on the same page and we're getting covered what we need to get covered. So until next time, I'll see you in class.